Our galaxy is made up of some 400 billion stars and at least 100 billion planets. How many are like Earth? With an atmosphere, complex geology, flowing water, and abundant life. Astronomers are seeking answers in countless photons racing past the Earth. And in whole new theories about how planets form and evolve. What they are finding has only sharpened one of the oldest debates in science. Is biology a powerful and inevitable byproduct of cosmic evolution? Or is life rare in a galaxy shaped by violence and mayhem? For millennia, we have locked our gaze on the heavens, hoping for a sign that life exists somewhere beyond Earth. In modern times, the search for life-bearing planets has become a central quest in a new age of astronomy. Giant observatories, equipped with a new generation of precision instruments, now allow us to detect planets in solar systems across the galaxy. And there's a whole new way of seeing that has vastly expanded the search. Earth in the 21st century. Computers increasingly shape the way we communicate, learn, travel, grow food, buy and sell, make things. The amount of processing power we can put on a computer chip doubles every 2 years. This trend, called Moore's Law, has turbocharged the pace of scientific discovery. Vast centralized supercomputing facilities have sprung up to search for patterns, hidden signals, in the torrent of data now streaming in from telescopes. Astronomers, once consumed with taking photographs and making measurements in cold observatories across countless lonely nights, now write computer programs, analyze data, and build models that simulate the complexities of star and planet formation. Far from settling the question, are we alone? Their discoveries have reignited one of the oldest disputes in science. To the Greek philosopher Aristotle, a perfect planet Earth sat firmly at the center of a small, orderly universe. universe beyond was utterly unpopulated, at least by any creatures other than gods. Not everyone agreed. Epicurus of Samos and his followers imagined an infinity of inhabited worlds among the stars. An ever-evolving cosmos gave rise to a boundless diversity of creatures. So too, for the modern descendants of Epicurus, our galaxy is filled with life-bearing worlds and potentially alien civilizations. We just have to find them. Astronomers have already determined that stars like our Sun are not uncommon. That planets the size of Earth, at the right distance from their parent stars to support liquid water, could number in the billions. Yet, a very different view has also taken hold, reminiscent of Aristotle. Biology is so complex, requires such stable conditions, and so much time, that Earth may well be an anomaly, a rare oasis of life in a desolate universe. Who is right? Back in the early 1960s, the astronomer Frank Drake, a modern-day Epicurean, theorized that signs of alien intelligence may well be streaming by us in the form of radio signals. Employing a radio telescope at Green Bank, West Virginia, he targeted two nearby stars, Epsilon Eridani, an orange star just 10.5 light-years away, and Tau Ceti, a yellow star about 3/4 the size and mass of our Sun. Since Drake began his work, the search for extraterrestrial intelligence, SETI, has expanded to hundreds of astronomers, thousands of stars, and a wide range of radio frequencies. Searchers have checked and rechecked Epsilon Eridani, Tau Ceti, and many other nearby stars. So far, after 6 decades of searching, they've found no repeating messages or anomalous signals. But they haven't given up, because there are so many more places and different new ways to search. Even as Drake looked for signals, other observers began looking for signs of planets themselves. The Dutch-American astronomer Piet van de Kamp sought evidence in the light of stars. After comparing photographic plates taken over 3 decades, he found that several nearby stars seemed to wobble, as if tugged upon by unseen massive companions. In particular, Barnard's star, a red dwarf in the neighborhood of our Sun, showed enough movement for Van de Kamp to claim he'd found an orbiting planetary system. He spotted other nearby wobblers, Lalande 2185, 61 Cygni, and Epsilon Eridani, the 3rd closest visible star to us. Van de Kamp's findings did not stand up to scrutiny. An error in the telescope itself doomed his results to wide rejection. But his gut feeling that the stars in the Milky Way host an abundance of planets took hold. And yet, what astronomers began to see is not what they expected. In the winter of 1991, engineers at the Arecibo Radio Telescope in Puerto Rico had noticed structural flaws in the colossal instrument. They'd ordered it frozen in position. This limitation gave astronomers Alex Woljan and Dale Frail the time they needed to observe a type of collapsed star, a rapidly spinning pulsar. Most pulsars spin very fast, emitting a flash with each revolution. One of their targets flashed about 6.2 times each second, but its timing was not predictable. It seemed to flash faster and slower in a complex pattern best explained by the gravitational tugging of two dense rocky planets. A third, much smaller world would later reveal itself. 3 burned-out zombie planets orbiting the corpse of a dead star. These are not the only pulsar planets out there. The oldest known planet, called Methuselah, rides above the Milky Way, at more than 2.5 times heavier than the largest planet in our solar system, Jupiter. Methuselah lumbers along in a 100-year orbit around a pair of dead stars, a white dwarf and a pulsar. These discoveries became part of a wider challenge to theories about how solar systems form and evolve, and how planets like Earth come to be. The reigning idea goes back over 2.5 centuries, called the Solar Nebular Model. This universal model is set in motion by the explosion of a giant star. Shockwaves from the blast cause a massive cloud of hydrogen gas to collapse. This computer simulation shows the remarkable events that follow. Huge volumes of dust and gas begin to stream into the center of the cloud. The tighter the cloud is packed, the more it heats up. A storm erupts, a raging hurricane of dust, gas, and ice crystals. In its eye, as temperatures rise, a star ignites. As matter flows toward it, the central region becomes a vast rotating disk. This disk is shaped by fierce hot winds from the newborn star, which push lighter gases to the outer zones, while leaving dust and rocks to dominate the inner zone. As the winds die down, planet formation begins. Beyond a certain distance, called the frost line, planets form quickly, growing large as they scoop up gas, dust, and ice. Inside the frost line, dust grains and rocks coagulate into solid bodies called planetesimals, most perhaps a kilometer wide, but some much larger. As they collide or merge, they form the planets we know today. In time, 8 emerge. to spin peacefully around the Sun ever since. If our solar system was any guide, astronomers expected to find rocky planets similar to Earth, Venus, and Mars in the sooty inner zones, where iron and silicon would melt and flow together to make solid planetary cores. Cool gas worlds, like Jupiter and Saturn, would orbit farther out in the frosty zone, where ammonia, methane, and water condense into small planets that grow large by gravitationally sweeping up lighter elements. Even further out, icy titans like Neptune and Uranus would crystallize after most of the gaseous hydrogen had been captured by the older, bigger planets. It didn't take long for the data to explode this conventional understanding. As a new age of planet hunting unfolded, looking into the southern constellation of Pictor, astronomers examined an infant star and detected an extra-large newborn planet. The star, Beta Pictoris, is twice the size of our Sun, 50% hotter, and almost 9 times more luminous. Its dense solar disk extends some 4 times beyond the orbit of our Pluto. Passing stars have been tugging on the disk, producing waves of turbulence. The planet, in an orbit twice Jupiter's distance from the Sun, is adding to the chaos. A NASA simulation shows a top view. The planet's gravity is hurling a stream of debris on a spiral path toward the star. A side view shows pressure waves created by its slightly tilted orbit. These waves ramp up collisions between icy and rocky bodies all through the disk. New models of solar system formation would have to take into account a host of factors at work in places like Beta Pictoris. The size of the solar nebula, the type of parent star, external influences, and the interaction of planetary bodies. Astronomers saw this dynamism at work as their planet discoveries piled up. Several teams focused on detecting wobbles in the light of stars caused by orbiting planets. As the star moves toward us, then away, it will change color, shifting from blue to red and back to blue. This can reveal planets orbiting very close to their stars, even if they lie very far away from us. In October 1995, Swiss astronomers Michel Mayor and Didier Queloz used this radial velocity method to examine the star 51 Pegasi, 50 light-years from Earth. 51 Pegasi is like our Sun, but 23% wider and 11% more massive. Wobbling motions in this star's light implied the presence of a giant planet, 47% less massive than Jupiter, but 1.5 times its size. Dimidium, as the planet is now called, defied all expectations. It sits in an orbit that is 8 times closer to its star than Mercury is to our Sun. this close-orbiting gas giant is hotter than Jupiter by at least 1,500 degrees Celsius. How did it get into such a perilous position? The planet at 51 Pegasi was only one in a string of oddball worlds found patrolling their inner solar systems. Large rocky planets lined with deep oceans. Small gas planets. Worlds covered in ice. Or lined with flowing lava. With discoveries like these, it was our solar system that began to seem like an anomaly. To understand the full range of planet types and how they formed within larger planetary systems, astronomers needed to target entire populations of stars and to discern details on a finer scale. In 2009, astronomers developed a new planet hunting strategy, combining spacecraft, telescopes, and supercomputers. Would it show just how unique Earth is? Or would it tip the scales toward the Epicurean model, a galaxy filled with inhabited worlds? Astronomers pointed the remarkable Kepler telescope at a group of about 500,000 stars, up to 3,000 light-years away. Their aim: to detect the slight dimming of a star when a planet sails across its face. For the technique to work, the planet must orbit along the line of sight between star and telescope. Using this transit technique, Kepler astronomers, with the help of citizen scientists across the World Wide Web, spotted nearly 2,700 new planets. Kepler's successor, the Transiting Exoplanet Survey Satellite, TESS, sweeps across almost all of the sky, looking at the brightest stars near Earth. But the types of planets TESS is revealing swings the pendulum back toward Aristotle. Transit surveys like these tend to find big planets orbiting close in to their stars. These missions, working in concert with the Hubble Space Telescope and ground-based observatories, have turned up still more hot Jupiters similar to 51 Pegasi. Some, facing powerful solar winds, are rapidly losing their atmospheres. Based on the Kepler data, scientists estimate Jupiter-sized planets and larger make up just under a fifth of all planets. The most prevalent type, at just over 50% of all known planets, is Neptune-sized, with rock or ice cores, surrounded by atmospheres of water, ammonia, and methane gas. Some theories suggest that deep inside, boulder-sized carbon diamonds rain downward toward their rocky cores. The ones detected so far sit close to their suns. They may be former Jupiters that lost mass, or gas giants that were flung inward by larger cousins. But in the data, at a point smaller than about 2 Earth radii, this class of mini-Neptunes gives way to dense, rocky worlds that dwarf our planet. These super-Earths make up 18% of exoplanets discovered so far. Among them, Kepler-22b is a super-Earth revolving in the habitable zone of its star. This planet may be a water world, with a deep global ocean clinging to a massive rocky core. Orbiting close to the star 55 Cancri is a rocky planet almost 8 times more massive than Earth. Its surface is a scorching 2,000 degrees Celsius. Kepler-452b has an orbit size close to that of Earth, and a parent star similar to the Sun. But the planet is some 5 times larger than Earth, so it's likely a cloudy world more like Venus. Then there are the Earth-sized planets, about 11% of the total. Earth-sized does not make them life-bearing. Consider these planets discovered by the TESS satellite. HD 21749, 53 light-years from Earth, is an orange K-type star 70% the size of our Sun. Its planet C maintains such a close orbit that its year is only 8 Earth days long. Its surface is rocky, likely hovering around 400 degrees Celsius. Neighboring Planet B is a hot mini-Neptune, 23 times the mass of Earth. Within a deep layer of clouds, temperatures average around 150 degrees Celsius. This planet, 1.3 times the mass of Earth, closely orbits the star LHS 3844. With a year lasting only 11 Earth days, its surface would be lined with pools of lava. Finally, the Sun-like star Pi Mensa hosts a planet twice the size of Earth. Its surface temperature is over 900 degrees Celsius. Still, as observational and computational techniques advance, there are glimmers of hope for finding Earth-like planets. Red dwarfs are the galaxy's most plentiful star type. They are hard to see, lightweight, cool, and much fainter than the Sun. Their planets orbit close in, their years rushing by in just a few days. Among them, Proxima Centauri, the closest star to our Sun. With barely 12% of the Sun's mass, it's only 2% as bright. After extensively studying the star for more than 18 years, astronomers have confirmed at least one Earth-sized planet. Proxima Centauri b completes an orbit in a little more than 11 days. It revolves at the distance where water could be liquid, just like Earth. Like many red dwarfs, Proxima Centauri has a stormy temperament. Large flares blasting with deadly ultraviolet, X-ray, and gamma radiation, likely eroding away any atmospheres its planets may have. Meet Proxima Centauri b, part of a breed of so-called eyeball Earths. These planets orbit so close to their parent stars that they become gravitationally locked, with one side facing perpetually in and the other out. One side is always arid and scorched by solar flares. The other, enshrouded in thick ice. Can a watery ring, with fertile land and life forms, exist in the twilight zone between them? Here is another candidate. TRAPPIST-1 is an ultra-cool dwarf star that hosts at least 7 planets, all bunched into close orbits. All are made of rock, but with densities that suggest an abundance of water. At just 11% the diameter of our Sun, this star puts out just 5/100ths the Sun's light. Fortunately, there is another source of heat. Like tussling siblings, the planets jostle one another's orbits. Tidal friction causes them to heat up from within. Those closest to the star are likely steamy and hot. Those farthest are icebound. The fourth planet out, slightly smaller than Earth, has the potential for liquid water. You probably won't find an advanced civilization here. In time, astronomers using space telescopes or ground-based instruments will widen their discoveries to include more planets farther from their stars. What they have found to date has already transformed theories of how our solar system formed, while dramatically altering the odds that we will find other life-bearing planets. Soon after our star ignites in this new view, Jupiter forms in the icy, gas-rich region beyond the frost line. It quickly cuts off the flow of matter to the inner solar system, slowing the formation of rocky worlds. Scientists have used supercomputers to project Jupiter's path amid countless small objects that fill the early solar system. The rings show the orbits of myriad would-be planets. Flashes mark collisions between them. The blue ring tracks the orbit of Jupiter. As it grows, Jupiter increasingly responds to the gravitational pull of the growing Sun, as well as the pushing and pulling forces from Saturn. Its orbit begins to shrink. Named for the turn a sailboat takes into the wind, scientists call Jupiter's inward move the Grand Tack. What the rising giant does not swallow, it flings out of the solar system or pushes toward the Sun. Chaos reigns as once smooth orbits turn into a disordered swarm. The simulation shows Jupiter reaching the orbit of present-day Mars. At this time, Saturn begins to pull it back out. Jupiter's grand tack would have dramatically reduced the mass of the inner solar system, If a super-Earth had formed, it was likely obliterated or driven into the Sun. From then on, the planets that formed or survived were bound to be relatively small. Ironically, Jupiter's destructive foray may have sowed the seeds of life by ferrying in large numbers of icy bodies. Destructive impacts continued, possibly bringing an end to the life-bearing chances of Mars. Earth was not out of the woods. Scientists theorized that early in its life, our planet was hit by a wayward Mars-sized world called Theia. Instead of destroying the young Earth, the angle of impact created a splash of debris that would coalesce into the Moon. Over time, the Moon's gravity acted to slow Earth's orbit and steady its spin. Tidal effects from the Moon's gravity churned the seas, helping to create conditions for life to emerge. Jupiter continued to serve as a benefactor. Working in tandem with Saturn, the gas giant shoved Uranus and Neptune off to the edge of interstellar space. That disrupted the orbits of millions of comets, flinging them toward the Sun. These icy projectiles are thought to have delivered massive amounts of water to our fledgling world. Ironically, one of the very first planetary systems to be examined by both Pete Van de Kamp and Frank Drake turns out to be arranged remarkably similar to our own. Epsilon Eridani has a cloud of icy debris left over from the system's formation in about the same place as our Oort cloud. A second disk of rocky bodies, equivalent to our Kuiper belt, and a gas giant planet at the outer edge of a ring of asteroids, like our Jupiter guarding our main belt. Astronomers don't yet know, but there could be a world like ours. The search for other Earths has long focused on the habitable zones of stars, where Earth-sized planets might settle into stable orbits. There, they'd have time to develop atmospheres, ocean currents, volcanism, and other factors that helped spawn life here. But the tangled history of our solar system shows that making a life-bearing planet is a matter of rare circumstance and considerable luck. Accordingly, some astronomers are seeking to redefine the search, focusing instead on finding the specific conditions that could support life. The most habitable planets, they say, may not be exactly like Earth. In a class all its own, a super-habitable planet could be about 1.5 times the size of Earth. It orbits an orange-colored K-dwarf star, cooler and longer-lived than the Sun. Set in the habitable zone of its star, the planet is lined with abundant water. A molten interior spins off a robust magnetic field. Together with a thick atmosphere, it deflects cosmic rays and solar radiation that pose a danger to life forms. Geological activity produces a patchwork of dry landforms, kept low by erosion. With stable conditions over long periods of time, the chances are good that chemistry and energy can come together to spawn life and generate a habitable climate. From the thousands of extrasolar planets discovered so far, scientists have distilled a list of 24 super-habitable planets with these general characteristics. How will we know if there is life there or on any other candidate? Future space telescopes will be equipped with instruments to search for oxygen, methane, and other markers of biology as starlight filters through their atmospheres. Giant new ground-based observatories may take actual pictures of planets, opening a window into their rotation rates, climate, seasons, oceans, even the presence of vegetation. In the absence of evidence like this, a skeptical follower of Aristotle may conclude that our planet remains wholly unique. But the new Epicureans, with ever more powerful technologies, hold to a different vision. They believe the sheer number of planets in our galaxy means we must not be alone. If our world developed intelligent life forms curious about their place in the universe, then so too did another. Even now, its inhabitants may be examining images of a yellow G-type main sequence star somewhere in the Milky Way. They see a tiny pale blue dot tucked into a remarkably circular orbit. Will they wonder if they have found that other Earth? Perhaps with intelligent life, able to communicate across the voids of space? Or will they wonder, after poring over their data and running planetary formation models, is it big enough or special enough to support life?